for the Nuclear Solutions Institute Colloquium. Sorry, position. He's going to give a colloquium today. So Jeremy Holt is coming from University of Washington now. He got his Bachelor of Arts from Flint, I think it was. But he just realized it's triple. He got philosophy, math, and physics all together. So that's pretty impressive. Then he went to Stony Brook to do his PhD, where he got the Max Dresden Prize for the best thesis. From there he went to Munich for a couple of years, 4 years, and then a research associate at UW, and now he's a assistant research professor at UW. So today he's going to tell us about structure and dynamics as related to Earth and the stars.
Okay, thank you very much, Dan. Okay, so good afternoon, and thank you for having me here. So today I'm going to explore connections between nuclear dynamics at the femtoscale and astrophysical phenomena on a very macroscopic scale. So now in most cases, the largest nuclear physics uncertainties are associated with the properties of neutron-rich nuclear many-body systems, which therefore are going to be a priority in nuclear science research in the coming decade. So for those of you not working in nuclear physics, and especially for the graduate students in the audience, I want to motivate some of the main topics by taking you through the life cycle of a massive star. So stars with masses greater than about 8 times that of our sun achieve sufficiently high temperatures late in their lives to fuse elements up to iron. So iron sits at the top of the food chain with one of the largest binding energies per particle of any nucleus, and therefore additional fusion reactions are thermally suppressed. Now, very shortly after iron fusion begins to build up in the core of this massive star, and it produces no new energy. In fact, the only thing that prevents the core from collapsing under its own gravitational weight is electron degeneracy pressure. However, once this core reaches a mass of about 1.5 times that of our sun, then this electron pressure is no longer sufficient, and in a fraction of a second, the core collapses. So the only thing that prevents the immediate formation of a black hole are strongly repulsive nuclear forces at short distance scales, which first halt the contraction and then create a rebounding shock wave that tries to explode the star. So typically, the shock wave doesn't have sufficient energy, but during core collapse, protons and electrons are fused together into neutrons, producing copious numbers of neutrinos, and these guys can re-energize the stalled shock wave and lead to successful explosions. So we immediately see the importance of nuclear physics in understanding core collapse supernovae. The nuclear equation of state governs core bounds and the energy of the subsequent shock wave. And neutrino interactions in a hot, dense, neutron-rich environment actually govern whether or not these stars actually explode. Now, core collapse supernovae are one of the possible astrophysical sites for the formation of about half of the heavy elements beyond iron via the so-called R process that I'll talk about a little bit later. So we don't actually know the exact astrophysical site of the R process, but whatever gets ejected from the supernova explosion gets recycled into additional stars, and then this cycle continues. But what's left over after the supernova is a superdense object, either a black hole or a neutron star. Neutron stars are extremely tiny. We typically observe them as radio pulsars. And once they're born, they simply give off energy for the rest of their life. They don't create any new energy, and they mostly radiate in the form of neutrinos. But that might not be the end of the story, because binary systems can survive supernova explosions. And particularly interesting are the properties of neutron star binaries, not the least of which because these could also be a site of the R process when these two neutron stars eventually merge. Okay, so what are the main physics questions that are sort of driving contemporary research in this field? Well, in the case of core collapse supernovae, we want to know what are the mechanisms that lead to successful supernova explosions. What can the detectable neutrino signal tell us about the inner workings? Try to stay out of the way of you guys on the left. What heavy elements are synthesized in this neutrino-driven outflow? The study of neutron stars is motivated really by our curiosity to understand the densest observable state of matter in the universe. So what exotic states can we have in the core of a neutron star, and how would that leave an imprint on the maximum neutron star mass? Neutron star mergers are particularly interesting because they could be they're expected to be the source of detectable gravitational waves, and in fact, it's expected that the neutron star equation of state will leave an imprint on this gravitational wave signals. And then finally, what heavy elements are synthesized in the dynamical objective. So in order to answer these questions, as well as many others, is going to require the combined efforts of 4 different communities in physics. So astrophysicists are studying neutron stars and core-collapsed supernovae using traditional ground-based telescopes, space-based satellites. But then there are these burgeoning fields of neutrino astronomy and gravitational wave astronomy that are going to try to make discoveries in this field as well. Astrophysical simulations are reaching very sophisticated levels, but they need inputs from nuclear physics. And much of my talk is going to focus on recent improvements in our models of both nuclear forces and the relevant nuclear microphysics that is fed into these astrophysical simulations. But nuclear theory isn't enough. There are specific regions in the parameter space, particularly at very high densities or at very low densities, where nuclear theory is challenged. And for this reason, nuclear experiments are going to be key for helping us extrapolate our reliable theories into regions where they're currently challenged. Okay, so what do the simulations need from nuclear theorists? Well, I think 3 main things. So first of all, they need a consistent approach to nuclear microphysics. So the equation of state has to be consistent with the neutrino transport. Otherwise, the simulations will develop bugs and break down. So we also need to be able to reliably extrapolate away from the valley of stability, where you have roughly equal numbers of protons and neutrons, into regions that are highly neutron-rich, that are relevant for these astrophysical scenarios. And then finally, quantifiable uncertainty estimates, so that we really have some idea of how good our calculations are. So I think in the last decade or so, chiral effective field theory, which is a new description of nuclear forces and many body effects, can provide the foundation for these types of theory inputs to astrophysical simulations. So in the first part of the talk, I'm going to describe this theory. But first I want to tell you what the traditional approach to nuclear forces and nuclear dynamics was up until about the year 2000. So the traditional models are based on one boson exchange models of nuclear forces. So just like charged particles interact through the exchange of virtual photons, nucleons were expected to interact through the exchange of virtual mesons. So you might already see a problem. There are lots and lots of mesons. So you might think of just taking the lightest mesons, the couple strongest to the nucleon. And those would include such mesons as the pion, the rho, and the omega. And they all basically have something like a Yukawa type interaction, which is a Coulomb, but exponentially suppressed by the relevant mass of the meson. Now, these models had some deficiencies and some problems, mostly related to the dynamics at short distance scales. So in particular, you would have the excitation of heavy mesons, nucleonic resonance excitation, and we don't understand in these cases really how well these nucleon resonances couple to complicated or more heavy mesons. Also, there's a sort of practical problem, namely that these interactions gave rise to nuclear forces that were very strongly repulsive at short distances, which precluded any kind of perturbative treatment. However, in the last decade, a new description of nuclear forces and nuclear dynamics has arisen based on the notion of an effective field theory. So I think of effective field theories as doing physics from next to first principles. Of course, a first principles description of nuclear many-body forces would start with the QCD Lagrangian describing quark and gluon dynamics with its approximate chiral symmetry. But this is almost never practicable for nuclear many-body systems. The idea, though, is to construct instead a low-energy effective theory for the relevant degrees of freedom. So namely, the stable nucleons as well as the lightest mesons that give rise to the nuclear force, the pions. And when you construct this effective theory, you simply write down the most general set of pion-nucleon interactions that are consistent with the symmetries of your underlying theory. Now, one of the problems is that you have an infinite number of terms, and so you need some way of organizing these various contributions. So in the case of strong interactions, we take advantage of the symmetry breaking property of QCD. So what do I mean? So if we look at this potential on the left, it's manifestly rotationally symmetric. And if we try to excite a quantum particle in this well, it takes a discrete amount of energy to excite the system. This potential on the right is also rotationally symmetric, but something is different. Namely, if we put a particle in this well, they would have to choose a position. And in some sense, that's breaking the symmetry that was in the potential to begin with. Now, Goldstone showed quite generally that whenever you break a spontaneous symmetry, then there exist excitation modes that require arbitrarily little energy to excite the system. Namely, you can kind of rotate the particle around this degenerate set of minima. So in the case of QCD, we identify these low energy excitation modes with the pions. And that tells us two critical things. First, that pions are light, which, okay, actually we already knew that for decades, right? But now we think we understand why theoretically. And second, it tells us that pions interact weakly at low momenta, sort of a generic feature of these Goldstone boson type modes. So with these two features, we can then construct order by order in powers of a light energy scale, meaning something like nucleon momenta and pion masses, divided by a heavy scale corresponding to these next most important mesons, various contributions to nuclear forces. What the theory doesn't tell us is what happens at short distance scales, right? So this type of physics is encoded in, the excitation of heavy mesons, complicated nucleonic resonances. It's all very complicated. The strength of the theory is that we don't really care what happens. We simply write down the most generic set of contact terms and fit them to experiment. And in the case of two-body forces, typically fit to nucleon-nucleon elastic scattering. In the future, maybe we can fit to lattice QCD. There are also short-distance three-body forces, which here we fit to the binding energy and lifetime of the tritub. But I just want to emphasize that once we fit the short-distance dynamics, then all of our calculations for nuclear many-body systems are pure predictions. And the theory either works, or we have to go to the next chiral order. So I like to think, what arises is this inward bound approach, description of nuclear forces, where each successive chiral order is probing deeper and deeper into the structure of the nuclear force while resolving more and more of these fine short distance details. I like to think of these effective field theories in terms of a simple mechanical model. So namely, if you take just a regular physical pendulum and you introduce a small amplitude, high frequency oscillation of the pivot point, then something interesting happens. So namely, the pendulum is stable about its inverted position, and small perturbations of this new stability position result in harmonic motion about the inverted point. So you could go and solve this somewhat complicated differential equation. So this is what Mathematica gave me. And you'll see that the exact solution has all of these fine distance wiggles. But it sort of obscures the nice harmonic motion that we observe on top of this. Kapitza showed in the 1950s how to understand what's going on. So he showed that if you decompose the motion into a slow and a fast component, and then time average over the fast component, you'll get an effective potential for this slow component, which then has a much simpler simpler differential equation you have to solve, and it can reproduce exactly the same harmonic motion, just without all of these irrelevant short distance details. So this is how I like to think of effective field theories. We're sort of integrating out these small distance fluctuations, and we're only probing nuclear forces at a very coarse resolution scale, and that gives us a simpler description of nuclear dynamics. So what are some of the successes? Well, here I'll show you some calculations using realistic 2- and 3-body chiral interactions, probing the limits of stability for calcium isotopes, or at least the limits of our experimental knowledge. So they studied calcium with neutrons up to 31 to 34, which previously weren't well constrained experimentally, and the predictions from chiral effective field theory are shown in blue. So these came out in 2011, the theoretical predictions, and then the experimental results at TRIUMPH and CERN lie exactly on top of the theoretical predictions for these neutron-rich calcium isotopes. So I think we have I think this sort of exemplifies that we can trust these types of theories in extrapolating to the neutron-rich parts of the periodic table. My all-time favorite example of the relevance of nuclear 3-body forces in this chiral effective field theory approach is the anomalously long beta decay lifetime of carbon-14. So which you might recognize as being responsible for the radiocarbon dating method. So the observed half-life of carbon-14 is about 6,000 years, but theoretically you would actually expect the half-life only to be on the order of hours. The only reason carbon-14 has such a long lifetime is due to a fine-tuned cancellation in the transition, this beta decay transition matrix element taking carbon-14 to the nitrogen-14 ground state. And this cancellation happens to a precision of about 1 part in 1,000, which results then in an amplification of the half-life by 6 orders of magnitude than you would normally expect. So yeah, this was a major challenge, at least from the perspective of microscopic calculations, and we were the first to show a few years ago the importance of 3-body forces. So here I plot the strength, the transition strength as a function. You can think of this as being the strength of the 3-body force, which we ramp up to its actual value. And when we do, we see that there's this dramatic suppression of the transition matrix element. So thereby indicating that 3-body forces were the main, the last missing piece of the puzzle in this carbon-14 issue. And a few years later, some supercomputer calculations solving the exact 14-body problem found the same feature, namely 3-body forces are responsible for this suppression. Okay, so we want to take these, these successes we've had in the case of nuclear few-body systems, finite nuclear systems, and apply them to astrophysical scenarios where we're thinking about things like infinite neutron matter. So first, let's talk about successful explosion mechanisms. So nowadays, we're living in an era of computationally intense 3-dimensional simulations of core collapse supernovae, binary neutron star mergers, and I think we no longer have the luxury of doing parameter studies. You can't take an equation of state, tweak it a little bit, and then run your simulation for 10 million CPU hours. Just not practical. So I think that provides one of the main incentives for really improving our nuclear modeling of these events. But you might ask, just how relevant are these changes to the nuclear microphysics? I actually think they're very important, and as evidence, I'll just cite this recent simulation of a 20 solar mass progenitor where they did a comparison study. So they did 2 supernova simulations, and all they changed is this neutral current neutrino neutron scattering cross-section by taking into account a strangeness contribution to the nucleon spin, which alters this axial coupling constant by about 20% for this reaction. Now actually just this 20% modification in the coupling constant was the difference between a failed supernova explosion and a successful supernova explosion for this 20 solar mass progenitor. Of course, these massive stars are very difficult to explode, right? You have all this matter that you have to blast through. But they found that this was actually sufficient. So I think that's not like the end of the story, right? We have to go back and make sure that all of our nuclear physics is at this level of precision, because clearly we see that these effects are making a difference. So what I've been working on over the last few years is developing improved equation of state models for supernova simulations. We know that soft equations of state typically generate more powerful shock waves, and we have to make sure that this is consistent with, with these neutrino modifications. The problem is that supernova simulations span an incredibly large region of the parameter space. So here I show the temperatures achieved in supernova, a typical supernova simulation. These are the baryon densities, and the color coding just represents the proton, the ratio of the proton number to the total baryon number in the simulation at that given point in parameter space. So we have to describe something like 3 orders of magnitude in the temperature, 8 or 9 orders of magnitude in the baryon density, and proton fractions ranging from about 0 to 60%. So this is very challenging, and to date we haven't constructed such an equation of state. What some people have done is compared the equations of state that are commonly used by the supernova simulation community and compared them to the predictions from chiral effective field theory. So here I show the equation of state of neutron matter, just the energy per particle, as a function of the density. And just to sort of draw your eye, if you had a non-interacting gas of fermions, the equation of state would look something like this. So nuclear forces, of course, are attractive, but neutron matter isn't bound. So the chiral effective field theory prediction for the energy per particle of pure neutron matter at 0 temperature is shown in this red shade area. And these Latimer-Swesty equations of state, which I would say are the most commonly used in the supernova simulation community, and you can see they're not even remotely within the error bands predicted by chiral effective field theory. So the relativistic mean field models do significantly better in some cases, but we need to explore more than just the neutron matter equation of state at 0 temperature. We need to go to finite temperature, look at mixed proton-neutron ratios, and see whether these models also match the constraints from chiral effective field theory in a much wider sense. So there are things that you can do. You can try to retune the parameters. These are both phenomenological models. They're not microscopic in any way. You fit to properties of finite nuclei, not just nucleon-nucleon scattering. So that's one option, but I think as a longer goal, what we really want to do is calculate microscopic equations of state for astronomical simulations directly from chiral effective field theory, plus consistent neutrino cross-sections. So in the next few slides, I'll tell you our progress on that front. So what you start with is a nuclear force model, and there's one additional parameter left in the model, namely the resolution scale at which you probe nuclear dynamics. So think about this Kapitza pendulum problem. Just how fine-tuned do we want to, or just what fine short distance details do we want to resolve? So there are significant difference in the nuclear potentials at different resolution scales. This is at the finest resolution scale. This is the order by order convergence of the equation of state in perturbation theory. And you see that there's some signs of convergence, but it's not perfect. However, our coarse resolution potential has nearly perfect convergence in many-body perturbation theory. So we think this is going to provide a solid basis for extrapolating to finite temperature calculations. We also looked at the equation of state of symmetric matter at 0 temperature. So this is now you have equal numbers of protons and neutrons at 0 temperature. And unlike neutron matter, which was unbound, symmetric nuclear matter is bound. And we know that regardless of the size of a nucleus, the inner region has a central density that's constant, regardless of the mass number. And that central density is about 0.16 nucleons per cubic Fermi, and the binding energy per particle in that system is about 16 MeV. So any calculation of the symmetric nuclear matter equation of state has to have a minimum at that point. So what do our calculations show? Well, first, if you only include 2 body forces, there's no hope. But when you include 3 body forces, the coarse resolution potentials, which we actually trust the most, come very close to the empirical saturation point of nuclear matter. If we include also our 500 MeV cutoff potential, then this gives us an uncertainty estimate in our calculation. But it's actually highly non-trivial to reproduce this fine-tuned balance between attractive nuclear forces and repulsive nuclear forces to get this energy per particle at the center of a nucleus. Just as evidence, I'll show you what the status of affairs was about a decade ago. These are the various saturation points of purely microscopic calculations. And as you can see, none of them, although one or two come close, but none of them actually go through the empirical saturation point. So this was a major challenge, but it seems to come out pretty well in chiral effective field theory without any additional fine-tuning. Okay, so that gave us confidence to go to finite temperatures and also arbitrary mixtures of protons and neutrons. So now we're calculating the symmetry, the free energy per particle of nuclear systems at these various isospin asymmetries, different numbers of protons and neutrons. Of course, from the free energy, you get everything. You get the pressure, the entropy, the chemical potential. And these are results. You can look at the evolution of the saturation point, but what's a little bit more interesting is what's called the symmetry energy. This is the difference between the neutron matter equation of state and the symmetric matter equation of state at a given density. And the symmetry energy is correlated with a number of important nuclear physics and astrophysics observables, in particular the radius of a neutron star. So here I show some phenomenological results by Latimer and Prakash, where they found that the quantity neutron star radius times the pressure of neutron matter at a given density is approximately constant. So if I tell you what the pressure of neutron matter is, which is actually just the slope of the symmetry energy at saturation density, then they'll tell you what the radius of a 1.4 solar mass neutron star to within about 10%. If I tell them the pressure of neutron matter at 1.5 times saturation density, they'll tell me the radius to within about 5%, and at twice saturation density to something like 2%. Okay, so these quantities, I think what's really interesting is the correlations between some of these quantities just of regular nuclear many-body systems and astrophysical objects like neutron stars. Now, you might have noticed, though, that in all of the calculations, I haven't really gone beyond about 1.5 and 2 times nuclear matter saturation density. So the reason is that as you compress nucleons more and more, of course, their energies and their typical momenta scales increase, eventually to the point where we no longer have a clean separation of energy scales that we started with and that was sort of the basis for our effective field theory expansion. So the effective field theories are limited up to about twice saturation density. And that's where I think experiments are going to be really critical for helping to extrapolate our theories, because in neutron stars we can reach 5 to 10 times nuclear matter saturation density. So in an intermediate heavy ion collision, you can create a very dense state of matter with large pressure gradients, and by analyzing the momentum distributions of the outflowing particle, you can try to go back and reconstruct the initial densities and pressures. Of course, that's actually model dependent. You have to solve something like a Boltzmann transport equation. And actually, there's important nuclear microphysics that goes into these transport equations, because this symbol E represents the energy that a nucleon or a cluster would experience as it propagates through a nuclear many-body system. And that's something that you either have to build a model for, or you have to calculate it from first principles. And one thing that I'm working on is trying to calculate the single particle potentials from chiral effective field theory, and hopefully reduce some of these uncertainties associated in the analysis of the equation of state from heavy ion collisions. So this was an analysis of the pressure as a function of the density. So these were quite high energy collisions, which allowed you to reach quite high densities. But also the low density regime is going to be important, as I'll talk about in a little bit. So another thing you can get from heavy ion collisions is information on the nuclear matter liquid gas phase transition. So experimentalists are confident, at least in the location of the critical endpoint for this first order liquid gas transition. So experimentally, they have these values for the critical temperature, density, and pressure, and our theoretical predictions, again, which have no additional fine-tuning, are completely consistent with the experiments. Okay, so that's basically our progress so far on the equation of state for supernova simulations. We actually still have some things to do, especially with regard to the high density equation of state and the low density equation of state. But I think we're making good progress. So next I want to talk about the supernova neutrino sphere and implications for the late time neutrino detection and heavy element nucleosynthesis. Okay, so what is the R process? So R stands for the rapid capture of neutrons. So there has to be some astrophysical event that creates a huge flux of neutrons that are captured on seed nuclei, timescales much smaller than that of the typical beta decay half-lives of these elements. So during this event, you push nucleons away from the value of stability to the very neutron-rich region of the nuclear chart. This is just the proton number versus the neutron number. So the R process creates all of these elements from which we really know very little. Hopefully they'll be explored in next generation radioactive beam facilities, but right now we know very little. But we need to know lots of their properties to understand and to disentangle the possible site of the R process. So namely, we need masses of neutron-rich isotopes, beta decay lifetimes, neutron capture cross-sections. Currently, all we have are models. So we seriously need some experiments here. And that's the only way we're going to understand the formation of about half of the elements greater than iron, including some certain precious metals such as gold. Now, for a long time, core collapse supernovae were kind of considered as the ideal site for the R process, but recent simulations of these events show that that's not at all true. Okay, you just don't produce enough free neutrons among other problems, but one of the main problems is that you don't create enough free neutrons. So what actually determines the number of free neutrons? Well, it's actually these charged current reactions. Neutrino absorption on neutrons and protons in this outer ejecta that basically change protons and neutrons into one another. Now, as I mentioned in the beginning, right after core collapse, we have this hot proto-neutron star. Neutrinos are diffusing out. And the cross-sections for these reactions depend on the average neutrino energies as they reach the region of last scattering. This region of last scattering is called the neutrino sphere. We don't know the exact properties, but it's something like 40 to 80 billion Kelvin, 1,000th to 1/10th nuclear saturation densities, and it's extremely neutron-rich. So what sets the neutrino and antineutrino opacities in the proto-neutron star that governs where the neutrino sphere is. Except, if these neutrinos decouple later, then they'll have smaller average energies. If they decouple earlier in the matter, then they'll have higher average energies. And it's actually the spectral difference between the antineutrinos and the neutrinos, if it's greater than about 4 times the neutron-proton mass splitting, then you'll have sufficiently good conditions for the R process. So namely, the proton fraction will be less than about 40%. So it's actually really critical, the location of the neutrino sphere and the average energies of the neutrinos and antineutrinos coming out from this hot matter. Now, the neutrino sphere is actually dilute by nuclear physics standards, but nuclear mean fields are not necessarily small in this environment. And in particular, nuclear mean field effects, they alter the kinematics of charge current weak reactions that determine the neutrino opacity. Actually, mean field effects don't have very much influence on the antineutrino opacity. I'll skip that slide. So how does that happen? Well, nuclear interactions, of course, are attractive at low momenta, and the neutron-proton interaction is more strongly attractive than the neutron-neutron interaction. So in this hot neutron-rich environment, the spectrum of neutrons is lowered, same as that for the protons, but the protons experience a stronger attraction. So that changes the effective Q value for this neutrino absorption cross-section, which can have a significant effect on the mean free path. So also it'll affect the charge current weak reaction absorbing antineutrinos, but this is not super relevant. Okay, so what happens to the neutrino mean free path when we include the effects of these nuclear mean fields? So without any medium corrections, we have these black lines for the inverse mean free path for neutrino and antineutrino absorption as a function of the neutrino energy. So we used two models. The first was just a chiral two-body force at leading order in many-body perturbation theory, which we know isn't sufficient, but right now that's all we have. That's all the theoretical tools we have at the moment. We'll try to extend this in the near future. But then we also looked at a resummation method where we sort of account for nuclear interactions at all orders in perturbation theory. And with this non-perturbative method, we see actually a very large decrease in the neutrino mean free path, right? Increase in the inverse mean free path. So what does that do? That means that neutrinos are going to decouple later from this proto-neutron star, and therefore the spectral difference between antineutrinos and neutrinos is going to increase, which tends to enhance the R process. So these types of effects have only very recently been introduced in some simulations. They used different nuclear force models. Their effects were a little bit weaker than ours. But this is relevant not only for our process nucleosynthesis, but also for detecting these supernova neutrinos in our water Cherenkov counters for the next galactic supernova whenever it goes off. We should be able to actually maybe actually get some information about the neutrino sphere from the next galactic supernova. Okay, so now I want to turn our attention from core collapse supernovae to what's left behind. And neutron stars offer an interesting window into strong interaction physics. It's actually not obviously the case, though, because if we look at sort of a similar compact star, namely white dwarfs, so you guys might recognize Sirius. It's the brightest star in the night sky. It has actually a companion white dwarf. And now the feature of these white dwarfs, though, is that it's really just the electron degeneracy pressure alone that determines the maximum mass of a white dwarf. So interaction effects are negligible, thermal effects are negligible. All that matters is this combination of relativity and quantum mechanics that gives us the maximum compact star mass. So neutron stars are different. If you didn't notice, the neutron star's right there. So Sirius B has about the same mass as Sirius A, and this neutron star has about the same mass as the white dwarf. So neutron stars, they're very different because it was shown early on using general relativity, solving the hydrostatic equations for equilibrium, that if you had degeneracy pressure alone, then the maximum neutron star mass would only be 0.7 times that of the sun. And actually the only reason that neutron stars exist is due to strong nuclear forces. So it gives us, the maximum mass in particular gives us an interesting window into the dynamics of nuclear forces at short distances. So we actually don't know the maximum neutron star mass. It's one of the premier searches going on in astrophysics is trying to find the neutron stars with the largest mass, because that can really constrain our interaction models. So why is that? Well, here I just showed the generic anatomy of a neutron star. We actually think we understand pretty well the generic features. So there's this outer crust consisting of a lattice of neutron-rich nuclei, and it's separated from the inner crust, which is characterized by neutrons dripping from these neutron-rich nuclei. So here you can have a superfluid state of neutrons interacting in this background lattice structure. You can also have some really interesting features close to the crust core boundary. You're almost entering into some nuclear material science here. But once you reach the outer core, then basically all the solid structures dissolve, and you only have a liquid of neutrons, protons, electrons, and almost certainly muons. But what's found in the inner core isn't really well known. There were lots of theoretical speculations. You can have hyperons, deconfined quark matter, superconducting quark matter, meson condensates. So up until a few years ago, most neutron star masses were just 1.4 times that of the sun. And there was room for all of these exotic states. But typically when you introduce more exotic states in the core, that causes the pressure of the core to decrease. Now the core has to support all of the matter above it, and so in some sense the nature of this material tells us what the maximum neutron star mass is. And these exotic states tell us that we can't really have very massive neutron stars. In fact, there's a really close connection between the nuclear equation of state, particularly at high densities, and maximum neutron star masses. In fact, there's a one-to-one correspondence between the equation of state and the mass radius curve for a neutron star. Right, so you basically integrate the Pullman-Volkoff equations, and then as you're probing, into deeper and deeper densities, then you generate these higher and higher masses. But anyway, the idea is that if these mass radius curves, if you give me the mass, then I'll tell you what the radius of the neutron star is. And this is just obtained from these general relativity calculations. So a few years ago, though, really everything changed, namely with the discovery of a 2 solar mass neutron star. It was measured quite accurately using this method of Shapiro delay. So there was a pulsar system with a white dwarf companion. And every once in a while, the white dwarf comes between the neutron star pulsar and us, and it causes a gravitational delay in the pulsar timing signals that we receive. And if you can accurately match the pulsar timings to the Shapiro delay formula, then you can accurately determine the masses of actually both objects, both the companion and the neutron star. And this allowed a very accurate measurement of this 1.97 solar mass neutron star. So this was the result shown in their paper, where they showed that a number of different nuclear equation of state models were simply ruled out by this 2 solar mass neutron star. However, a lot of nuclear equations of state, typically that have sort of no exotic states in the core, these all survive, and they can give you maximum masses up to about 2.5 times that of the sun's. Okay, so in the future, though, what we want to do is not only calculate, maximum neutron star masses, but we also want simultaneous radius mass measurements, because that will allow us to pin down specific points in the mass radius curve. And as you can see, if we could get just a few simultaneous mass radius measurements, that would be an even stronger constraint than just this maximum mass. So there's actually quite a few efforts going on. There are a lot of different ways to try to measure radii of neutron stars, but these guys are really tiny, they're really faint, and it's a very difficult challenge. But one thing that's exciting about the field is all of the interesting ideas for how to make these simultaneous measurements. Okay, so in the last few minutes, I want to talk about neutron star mergers and look at these 2 ideas. So namely, how can the equation of state be printed on the gravitational wave signal, and what heavy elements are synthesized? So there is currently a race on to detect, or to make the first direct detection of gravitational waves. And advanced LIGO should be coming on within the next year or so. And if it does, we really expect to start seeing gravitational wave signals coming from compact binaries. So neutron star black hole, merger events. And these are coming from high frequency, very low amplitude gravitational wave signals. So just to try to impress you a little bit, advanced LIGO it's basically a Michelson interferometer with arm lengths of a few kilometers. And in order to detect these gravitational waves, they have to resolve fluctuations in these arm lengths down to about 1/1000th the size of the proton. I just find that amazing every time I say it. But anyway, so these guys are doing really impressive things. There are also other efforts. So ELISA, which is it's coming up in the more distant future. It's going to be a space-based satellite. There are some pulsar timing arrays that should be able to probe different sources of gravitational wave signals. But this is a really exciting field, and I think these compact binaries can be one of the first sources that might be detected. So here I just want to show you a recent simulation which shows the merger of two neutron stars after they've evolved for about 100 million years and lost energy due to gravitational radiation. Okay, so let me stop there. Okay, so these neutron star merger events are interesting for a number of different reasons. Obviously, gravitational wave detection, but in the case of nuclear physics, what happens just before merger is the smaller neutron star is tidally deformed, and this tidal deformation is equation of state dependent, and also it should show up in the gravitational wave signal, namely as an accumulated phase relative to if you just had 2-point particles. If you have extended objects, then you get these quadrupole deformations, and that alters these gravitational wave signals. And right now the estimates are that if you have on the order of tens of gravitational wave events per year, then you might actually be able to start doing some interesting neutron star physics and equation of state physics with these events. Also, it was shown quite recently that there are a lot of groups working on this. This is just a German group. So these tidal tails of core collapse, of neutron star mergers are really an ideal site for the R process. In fact, it's very easy to populate this final peak as well as most of this second peak. And this is basically all groups doing these simulations find that you have extremely neutron-rich environments, and it's actually quite easy to produce R process elements. But then, then the question begins, or it comes, these merger events take about 100 million years to finally give off enough gravitational radiation to come close and merge. So, how is this consistent with the abundance pattern that we observe today if these events take so long? So there's still some unsolved problems with respect to the R process, but these seem to be very encouraging. So in any case, I just want to wrap up and say that I think it's really an exciting time in this field, just owing to all of these different efforts from astrophysicists, those doing the simulations. I think there are interesting things happening in nuclear theory that I've tried to tell you about. And the last major piece, I think, are next generation radioactive beam facilities that should be coming online in the next 5 to 10 years. And this is going to fill in important information on these neutron-rich isotopes. And also hopefully also help us explore the physics of the neutrino sphere. So some things that I'll be doing in the near future is trying to merge these equations of state with those actually doing the simulations. Of course, we also need to calculate the consistent neutrino reactions. So far, what we've done wasn't really consistent with our equation of state model. We need to go back and do that. And also a better description of these nuclear mean fields for helping to reduce the uncertainties in model extractions of nuclear equation of state properties in these heavy ion collisions. So I'll just leave it there with this quotation from a recent decadal survey highlighting the need to synthesize nuclear dynamics at low or short distance scales with these astrophysical phenomena. Thank you.
Okay, so we have time for questions. Hello?
Yeah, can you go back to the experimental measurement of the massive function of R for neutron star? As far as I remember, there were two groups of data.
So this,
Yeah, one is around the R equal 11, other one is smaller r. Experimental data.
so I didn't show any experimental
Yeah,
data
but what's the
actually.
status of the experimental data?
Yeah. So so I was actually at a workshop 2 weeks ago devoted specifically to this question of the neutron star radius, and the consensus was that it's between 9 and 15 kilometers.
Okay, then I have another comment. You mentioned mostly results with neutron star. Another important constraint is to fit binding energy and radii of nuclei. And some of the
Absolutely.
interactions that fit nicely the mass 2 don't do that.
Yeah, absolutely. So you
And
can
they are
have the
very,
neutron.
very popular in calculations.
Yeah, exactly. So, right, so you're referring to the neutron skin thickness, right? I mean, that's correlated with the.
Not only
the
that,
rate-
some interaction were produced by neutron star people without paying attention how they do for binding energies and radii.
Okay, yeah, I completely agree that that's a problem. Yeah, right. I mean, it is difficult to calculate nuclear radii using the current methods that we have from in ab initio microscopic many-body theory. But yeah, experimentally.
No, I'm
we
talking
can-
about charge radius, which you know. very
Oh,
well.
charge rate. Okay, fine.
Joe?
So when you were talking about the neutrino transport and the effect of the mean field, it wasn't clear to me whether you had correlations and clusters in there or not.
No, we don't.
You don't.
Right. So we only consider, so the conditions that we assumed were such that you wouldn't expect to have clusters. So we took a pretty high temperature, about 8 MeV, and a reasonably high density of about 1/20th to 1/10th, maybe 1/10th saturation density.
Oh, but, I mean, Occam Schwenk was one of the co-authors on that paper, right?
Yes.
So he knows better. There are clusters at those densities and temperatures.
8 MeV, 1/10th saturation density.
Oh, yeah, and he knows it. So that was one question I had. The other is, I mean, you have a neutrino sphere in the supernova.
Yes.
You have neutrino surfaces in binary mergers, and they have, both of them you're talking about as a possibility for our process. Are the electron fractions the same in those two processes, or are they enough different that if we located the R process
I think
on the chart of the
environments-
nuclide, would it be different for the two? I mean, where is the R process, I guess is my question, on the chart of the nuclides? Is it different for those different scenarios?
Not sure I quite understand. So you.
No, I'm saying what set of nuclei do we go through and how neutron
Oh,
rich
they're
are
very
they?
different. They're very different.
They are different.
Yeah, absolutely. So the neutron star mergers push the R process curve much further into the neutron region.
Although most supernova models still really have a hard time exploding, it's still kind of on the edge. You can see how the material, the R process gets out of that by the gravitational collapse. But how does the R process get out of a binary merger? Where's the energy coming that throws it out?
It's really a tidal tail. So it's tidally. There are actually different ways, but sort of the paradigm is that it's ejected as the material starts to merge, and then the tails are not gravitationally bound.
So it's a hydrodynamic effect?
Yeah,
in the
it's
table?
hydrodynamics.
Also, if that's the case, you would expect in globular clusters where you will see more mergers of neutron stars to have different R process element abundances than in the field. Because in the cores of the globular clusters, the binaries get condensed because of three body interactions. And that causes in the middles of globular clusters something called, stops what's called core collapse. So you'd expect there are certain astrophysical environments, if this really is the case where our process comes from, that there would be difference in the iron to R process ratios in certain classes of stars.
Okay, that's very interesting. No, I wasn't, yeah, I hadn't been following this discussion in the case of globular clusters, but that's an interesting observation.
So, you commented about basically trying to set a resolution scale and averaging over the fine structure. And I understand the philosophy of that, and it makes a lot of sense. However, the contact interactions seem to exactly contradict that, in the sense that the contact interactions are, to the extent they're really treated as contact interactions, are really zero scale. And at that level, you're actually going to the extreme on the other side. So it seems to me you're mixing things in an inconsistent way.
Okay, I would say no. So so everything you said up until the final statement was correct, I would say. So let me just go back. This might help explain. I didn't actually go through it in the talk. So we do have a good separation of energy scales in this case, right? Q is much less than the mass of the omega. And if you simply do the expansion, then you get these, contact plus derivatives of contact terms. So the point is, this isn't the short distance dynamics isn't constrained. Well, okay, it's not constrained by chiral symmetry, so it's sort of a separate piece. But now, what we do once we have these contact interactions, in addition to that, we also have a regulating function, which will cut off these contacts at a higher resolution scale. So these contact terms, which probe sort of all momentous scales equally, effectively they do get cut off in our theory because we introduce
So you introduce
the
a
cutoff.
contact.
Yeah. Yes.
So that must be additional hidden parameters.
No, because it's okay. There's an order. So So exactly how we cut off the term, that can vary. Yeah, how smoothly it cuts off. Yeah, exactly. So there is one parameter. It's not tuned in any way. It's just chosen. And some people have, including myself, we have explored different cutoffs, different forms for the cutoffs. Yeah, but it's not fit in any way. It's not a fit parameter. It's just a choice.
So how's it chosen?
So
It sounds to me like exploring different choices is a poor man's fit.
No, so we don't explore the choices. So we actually there's a typical regulator. So we have the incoming relative momentum and the outcoming relative momentum. And if either of these gets large, then we want to cut off. It's just an exponential. So it's minus, so p squared over lambda. So this can be some. So yeah, we have the choice of both lambda, which I showed you the different variations, but then also the choice of just how smooth. So this would, this looks something like this, where this is our cutoff scale lambda. Right, and this gets multiplied by matrix elements, so P prime. Okay, so we don't explore different possibilities and see which one is best. Just sort of historically, we know we want this to be relatively sharp. So we take for the low cutoff potentials, we take a high power, say n equals 10, which makes this, pretty sharp. I mean, you could take the limit where it's effectively purely sharp, and then that would be some kind of model independent way of introducing this regulator. But I just want to stress that we're not doing any additional tuning behind the scenes. It's just kind of a random choice what this N is. We just want something that cuts it off relatively sharply.
Couldn't you fit this to reproduce the metric?
I wouldn't want to do that.
And then all your interaction can be just tune this and fit always the same point.
I mean, it's interesting to see what would happen if we generated different potentials with different, different values of N. But it's not, so I think that would go against, to actually use that as a fit parameter, I think would go against the philosophy. And I'm not certain that it would actually have extremely
It could
important.
be an excellent choice. I mean, you could have fit a two-body level just by choosing a different parameter. I don't know, I'm asking.
But you're still trying to use this as a fit parameter? I
It
would
is something strange, right?
I would be against using it as a fit parameter. I think that's just my stance.
In the realm of really obscure astrophysics, there's an object called a Thorndike star. And these are objects which are neutron star cores in stellar atmospheres. Thorndike showed that you could match the boundary conditions of neutron star to the atmosphere of a red giant. But there was no explanation for how stars would get in this situation.
I mean, are they accreting or?
Whatever,
Okay.
but there was no good way. But now one has been discovered, evidently. And I'm wondering, evidently, it sounds like no one is discussing this in your community, but this is a way of getting a boundary condition on the surface of a neutron star. Whether it's a meaningful boundary condition or not, I don't know.
So this is a theoretical advance.
No, there's actually one has been discovered
It's in
in
the-
the Large
okay.
Magic
Oh,
Clouds,
okay.
probably. That's
Okay.
There's an article a couple months ago, Phil Massey.
Oh, okay. No, I wasn't aware.
These may exist, and if they do exist, there are probably quite a few of them. So that may be a new channel for trying to figure out the boundary conditions of a neutron star.
Interesting. Yeah, thank you.
All right, well, if there's no other questions, just before we thank him, there is a seminar tomorrow if you want to know more details. It starts at 3 at the cyclotron. You're all more than welcome. 2:30? I think it's 3. Okay. Well, there'll be an email. We'll get the time right. So, again, well, thank you, speaker. I could have sworn it was 3.